So I guess we'll start today's session. About midterm statistics, I will explain it in the third hour, all right, together with the solutions. Okay, so today we're doing a very brief review of what you have explained last time, and then continue with a very elegant algorithm. Well, so there's one question. Oh, okay. Yeah. So you're right. So there's a typo on this page. This one should be does not. Thank you. So last time we talked about chores, right? We are dividing something which people do not like. And then we have some algorithms. For example, we can use round robin. Everyone pick one item which he or she likes most, and then in turns, right? And then we also introduce the so-called MV cycle elimination algorithm, which is trying to do the following. Now, every time one person will get an item, and that person basically does not envy any other person. Okay, so this one will get an item, but when this person does not exist, in other words, everyone envies some other person, then you can imagine there is a so-called envy cycle, right? So it can be A envies B, B envies C, C envies A. And then if there is such an envy cycle, then it will be good if we just shift the bundles along the cycle such that this cycle will totally disappear, right? Okay, now with this operation, we can further go on to process those cycles until in the end there is no cycle, and then where there's no cycle, again there will be one who envies nobody else, right? And then you can give him or her another item. So the algorithm just go on like this. And then last time we mentioned that if it's goods, right? So if it's the items that people like, then this algorithm, envy cycle elimination, can very naturally give you a so-called EF1 algorithm. So EF1, remember, it means that you do not envy other people if you are able to remove one item from other people's bundle. So this is for goods, right? For goods, you are allowed to remove one item from other people's bundle, and then you say, I no longer envy them anymore. Right? I no longer envy them. But for chores, the definition is slightly different, right? So for chores, we are removing items from the agent's own bundle, right? So after removing an item, this agent gets less. Now remember in chores case, getting less is good, right? So removing one item from his own bundle, after that, if he or she envies nobody else, then it's good. It's EF1. And then I see Ziao ask question, is this algorithm guaranteed to converge? Now actually, it's a good question. You mean the envy cycle elimination, right? So basically, well, it may need some proof, but it will definitely it will converge for sure. All right. You can see that actually one way to prove it is that if you do the shifting of the cycle, right, the bundle along the cycle, then everybody gets better, right, and nobody else gets worse. Everybody along the cycle gets better, and nobody else outside of the cycle gets worse. So after finite rounds, you will come to a stop, right? Because you cannot infinitely become better and better until zero. So basically there is a bound for that. Okay, yeah, good. Now, and then last time we say if we do this kind of envy cycle elimination for chores, there will be potential problem. So what's the potential problem? Now remember we say here for chores, because you are removing an item of your own bundle, then after you shift bundles along the cycle, there will be a problem because you are getting a different bundle after shifting. But this different bundle, if you remove one item, well, it may not be better than before, right? Total it's better, but removing one item may not be better. That's why if you still use the MV cycle elimination algorithm, there will be trouble because you cannot guarantee the EF1 property. Okay, so that's why in the last lecture we say, then we may need to use a new concept called top MV cycle elimination, which means that when you establish those MV edges, you are only creating those edges which indicates that this person envies some other one most, right? In other words, it's the red edges here, right? So black edge, for example, A3 envies A1, A3 envies A2, but A3 envies A1 more. And then in this case, we only keep the edge from A3 to A1, right? And then the black edge will be gone. Now, if you do this, then after the shifting, you will see some good thing happening. All right. So basically, if you swap the bundle of A1 and A3, then they should be happy, right? Okay. So the details I will not go into. In order to understand the whole thing, I would suggest that you can read the paper afterwards. All right. So these details, it's less likely to be totally understandable within the class for a majority of students. So I would say that for this part, you just need to know for now, top MV cycle elimination algorithm will always return an EF1 allocation for reasonable cost functions. So what are reasonable cost functions? They're monotone and combinatorial. Okay. Okay, very interesting question. Okay, Wing Zhong asked, will this algorithm be tested in exam? Now I will come to the exam part very soon. Okay, because now I have already a very clear scope of the exam questions. I will explain it in the third hour. All right. Okay. Now here for this direction, basically there are some open problems. For example, we don't know whether EFX allocation exists. Okay, so just now we are talking about EF1, right? So you can find EF1 allocation. But for EFX, which means that if removing any item from your own bundle, you do not envy others, right? So for EFX, people do not know whether that exists, even for additive cost functions, all right? And we also do not know anything about approximation algorithms. So that seems quite a big field to work on. Okay, now, but there are some good news. For example, if there are two people, then EFX allocation always exists. Okay, so for this one, any idea why two people EFX always exist? So EFX means I remove one item from my bundle, I will not envy the other person, right? Okay, very good. So now, actually, the point is, you can always find one which does not envy other person, right? So I will give okay. Now, because if there is because of envy, right? Envy, it's always something like I envy you, you envy me. So if there's a cycle, I swap, right? Now, if there's no cycle, then somebody is not envy the other person. But well, that argument probably only works for EF1 because well, now we are talking about EFX, right? No matter which item I remove, I will not envy. I will not envy you, right? Okay. Well, so it may not be that straightforward, right? Okay, but well, that's a good direction to think about. Okay. Now we will come back to it probably after we finish the whole session. Okay, to see whether well some answers will pop out. Okay, Nancy Yao answers. Everyone takes turn to choose the least chore for that one. Okay. Okay, so basically you're saying that probably you should arrange all the chores according to some order, right? Yeah, so then that one will be used in some of our future discussions about this topic. Okay, now for now, well, I think that probably we need some more time to think about this n equal to 2 case, although it's very fundamental. Okay, now actually this one, okay, what Xiao suggested may work for the second one, identical valuation. So what's identical valuation? Identical valuation means, well, for the same item, right? People think the same way towards that. All right. So for this one, then it probably works. Now the reason is you can order the items according to decreasing or increasing cost. So so here we are again using the so-called top cycle elimination or that type of algorithms, right? And every time you pick someone who does not envy other people, and then you would pick pick the item, right? Next item, assign it to that agent, right? So are we sorting all the items according to increasing cost or decreasing cost? Okay, we got increasing cost. Now well, so the first decreasing will get a bonus. Okay, so basically, why decreasing? Because well, we are trying to make sure the newly assigned item is the cheapest or has the least cost among all the items. Because this way, if you remove the newly assigned item, then this person who get the newly assigned item will be happy, right? Okay, so EFX says you remove any item, the agent will become happy. So if you remove the least cost item, he becomes happy. Then of course we remove any item whose cost is higher than the least one, and this agent will still be happy, right? So you are trying to assign items in the decreasing order of cost. Okay, you assign the heaviest cost item to some agent first, all right, and then gradually decrease the cost. The item's cost will decrease, and then this one, top cycle elimination, is still envy free up to 1, but that one is the cheapest one, right? The one with the smallest cost. Okay, then that means okay, removing any item, I will be happy, right? Removing the smallest cost, I will be happy. Removing any cost, I will be happy. So that EF1 directly becomes EFX, right? Okay, so this is something we are going to use very soon in our explanation in the coming slides. Okay, now of course there are also other special cases like a binary additive case where the cost is 0, 1 for all the agents, but they can have different opinion towards the same item. Okay, so you may also try to think about whether, well, what kind of algorithm will guarantee EFX allocation. So basically here we have two small exercises, right? One is n equal to 2, right? 2 people, all right? And then the second one is binary additive. Okay, so one of them, I will leave it as an in-class exercise. Okay, I think that the binary additive, this one will be more challenging. Okay, so maybe we can do it after class, not in class. Okay, n equal to 2 case, it should not be too difficult. Anyway, we only have 2 people, right? Okay, so this one I will leave it as an in-class exercise for part 2. All right. Now, for in-class exercise, just a side note. Up to now, there are already several questions I raised in class, right? And then there is also a tutorial, which I'm going to release very soon, probably early next week. Okay, early next week. And then those things together will become the in-class exercise part 2. And then I will open the link of submission very soon, also next week. Okay, yeah, the question, all right. So the question for today's in-class exercise is try to show EFX allocation exists when there are only 2 people, when you divide chores. Okay, so your task is to find or find an algorithm which can generate an EFX allocation. Yeah. Okay, so next one is the most interesting one, I promise you, in the last lecture. Okay, the last one says identical ordinal. What is that? So this one seems a bit artificial, but it turns out to be very useful. So this one says, in this case, every agent has the same opinion towards all items about their order. So for example, everyone thinks item 1, his cost is largest. Item 2 is next to it. Item 3 is further next to it. Okay, so their actual values, the actual cost values could be different. For example, my opinion towards the 3 items are 5, 2, 1, right? The other one, his opinion is 10, 6, 3. Okay, right? So different people have different values, but their order is the same. Okay, this is called identical ordinal. And Xiao is asking about the question. Yeah, so the in-class exercise is assuming, well, remember, n equal to 2. This version does not have any requirement about whether they are the same or not, or whether they are 0, 1 or not. They are arbitrary. Okay, they're arbitrary cost function for 2 people. Okay. Yeah, so Winchong asked, does identical valuation also lead to ideal? Yes, this is a special case of ideal, right? Ideal is more general than identical valuation, right? Because identical valuation, all the CI1 will be the same for all I, right? Okay. Well, I hope it's fine, because I will very soon go into the very, very nice property of ideal instances. Now, for this one, right? So we can find one example where you see agent A1 among the 6 items, the values are 4, 3, 2, 1, 1, 0. It's decreasing, right? And A2 is also decreasing, 3, 2, 2, 2, 1, 1. And agent A3 is also decreasing, 10, 3, 1, 1, 1, 1, right? Okay. So basically, you can see that, well, this is a special case for this ideal instance, right? Now, for ideal instance, so if we use the top NV cycle elimination algorithm, then it can return EFX allocation. Now, this one we already explained, right? Because, well, for identical one, we know that we can allocate the one whose cost is heaviest first, right? Now for IDO, actually, we can still do this because, well, there is one item who is valued most from all the agents, right? So this item C1, can be allocated first. Now, basically, the argument we use to derive the EFX allocation can still be used here for ideal instance, because in ideal instance, there is a common sense or consensus about which item is heaviest, which item is next, right? So this is a consensus. That's why if you follow this order, right, you allocate C1 first, and then C2, and then C3, then the resulting allocation will be automatically EFX, right? Okay, so the reason we already explained. So you see that, well, it benefits, right? We do have some preliminary analysis about sorting all the items according to their cost. So now for ideal instance, we can still sort the items according to the cost order, and then we can do this kind of top cycle elimination, top NV cycle elimination to derive EFX allocation, right? Okay, now now the reasoning, right, here we already explained. Now we come to some further definition for chores when we talk about proportionality. Okay, now remember that now, up to now, we have 2 major fairness measures. One is EF, right, NV-free. The other is proportional, right? So proportional in the chores setting, it will be also very similar. So proportional means the cost allocated to agent I is at most 1 over n times the cost of the whole set of items from the point of view of I, right? Okay, so this cost is less than or equal to 1 over n CIM, right? Okay, cost for agent I, right, is less than the average of this valuation. Now, this is proportional. Now, we can also define proportional up to one item. Okay, now here, proportional up to one item. Again, we are removing one item from the agent's bundle, right? So prop 1 says, okay, after I remove one item from my bundle, my cost is not too big, right? Okay. And then there's also a proportional up to any item, right? If we remove anyone, basically I will remove the one who is smallest cost, right? I remove the one who is smallest cost, I can still fulfill the average cost, then it's called prop X, okay? And then very naturally, prop X allocation is, prop X allocation is also prop 1, right? You remove the cheapest, now of course, the cheapest removal is good, then of course you remove one, the most expensive one, it will also be good, right? Okay, so this relationship we have seen it many times, even for goods. Okay, and then in a very recent paper, they proved that prop X allocations for additive valuations always exist. Okay, and then we come to the most interesting part of this topic. Okay, so there are basically two important parts here. Actually, when I'm going through it, we will mention something which has a potential to appear in the final exam. Okay, now one thing is this lemma, and this lemma says the following. It says if we have an algorithm that returns a prop X allocation for IDO instance, then we can design another algorithm for the general instance. Very easy. Okay, so that is indeed very, very interesting. So let's see how we show it. Now, you see that the following two tables, one of them is arbitrary instance, the other one is IDO, right? So the one below is IDO. And then what's the relationship between these two? Oh, very good. Okay, so we are sorting the cost of each person, right? So for agent 1, originally its order is 142301. We just sort it in decreasing order, right? Okay, and then second one also, we sort it in decreasing order. Third one also. Okay, now we transformed the general instance to an IDO instance. Now remember we said that for IDO instance, we have an algorithm that generates a proportional allocation, right? Proportion up to X, up to any item allocation. Okay, now suppose this allocation is something like this. Agent 1 got 4, agent 2 got 2, 2, agent 3 got 1, 1, 1. Is this prop X? Now let's compute the total value of each agent, right? So agent 1, its total value is 4 plus 3 plus 2 plus 1 plus 1, right? So that's 11. Okay, so 11, 3 people, average should be 3.6 something. Oh, but this one gets 4, right? It's slightly above. But remember, we are talking about prop X, so we can remove one item from his bundle, right? Okay, so that's fine, right? After removing, it gets nothing. And the second person is also good. 322211. So it's also 11, right? It's also 11. And then average is 3.66. And then he also gets 4. But again, you can remove an item. So only 2 left. So this one is also happy, right? The last one, agent A3, he got 3. This one is very obvious, right? He only gets 3. The total cost is about 17. So he's very, very happy. Okay. Now, let's see how to transform this solution to a solution for this instance, such that everyone still gets a prop X allocation. Now, first, let's think about it for a moment. Okay. How to do it? Now, something we would like to make sure, all right, because we are talking about prop X. So because we are removing one item, we try to make sure that each person, they get the same amount of items in both allocations. All right. So there are basically two criteria. The first criteria, in this general instance, we hope each person gets the same amount of items as the instance below. All right. So if, for example, agent 1 gets one item here, then he also only gets one item in this general instance. All right. So number of items should be the same. Right. This one thing. Second, what's the second one? Going to guarantee one. Now this one is a bonus. Okay. Up to now, I see some close answers, but didn't see a right one. Okay, I see cost should be less. I would treat Dutlev's answer as roughly correct, because the second criteria we are trying to make sure is that the total cost assigned to each person, they cannot be more. They should be less or the same. Okay, it can never be more. All right. And then okay, so Zheng Yan, I guess I will give you the one bonus here. Okay, so this one is a one bonus. Basically, you explain the algorithm. Okay, so well, yeah, although it may still be a bit distance away from the true algorithm, but I believe that the idea is already there. Okay, so just now we say that we want two criteria. One is the number of items allocated to each agent should be the same. All right. Second, the value. The value allocated to each agent should not be more. It should be less or equal. Now, if this is satisfied, then very likely, originally it's EF1. It is originally it's a prop X. Now it is still prop X. Well, but actually these two alone are not sufficient. Okay, so these two are only some high-level directions we try to guarantee. Okay, let me just pause for a moment. Let me just scroll back. Okay, now, so let's look. Well, I know that some of you also hate the idea a bit. So, well, let me just continue with the algorithm first. For those potential bonus, we can discuss about it a bit later. Okay. Now, what's the algorithm? In order to guarantee the number of items allocated to each person is the same, then we should somehow let the agent choose their items. All right. So in the ideal instance, they choose, for example, they are assigned 3 items. Then in the general instance, they should also be assigned 3 items. But the way we assign it should follow priority. So what's the priority? So basically, you see, agent 3, in the ideal instance, he has 3 ones, which is smallest, right? 3 ones. So basically it says that, well, agent 3, it should have a very high priority to pick items, because you see in the ideal instance, he gets 3 cheapest one. That's very good, right? Okay, so we somehow should allow him to choose 3 items in the first round. Okay, why? Because, well, you see, in ideal, he got 3 cheapest among all the items allocated to any people, right? Any agent. So we let this agent 3, to choose 3 items from the bundle, from the whole set. So if he choose 3, then which 3 does he choose? He will choose this one, 1, right? Okay, so the values the last agent choose will not change. but the correspondence to items will change. So basically now he chose C1, C3, and C4. Okay. Well, up to now, at least for this last agent, well, in this example, for this last agent, we can satisfy these two properties, right? You get the same number of items, 3 items, value didn't increase. Okay, actually, well, the values are all the same, right? Okay, so for this person, agent 3, very happy, right? Okay, now for other people, actually they're also happy. Why? Because for other people, in the ideal instance, after agent 3 picked 3 items, they lose 2, 1, 1, right? The second person lose 2, 1, 1, and first person lose 1, 1, 1, 1, 0. Okay, but in the general instance, they lose what? They lose 2, 2, 2, and 1, 2, 3. Okay, now what does it mean? It means that what they lost is better, right? Earlier, they lost the smallest cost items, right? But now they lost somewhat expensive items, right? So in the worst case, they still lose the smallest items, right? In the worst case, they still lose the smallest items. No worry, no hurt. But now it's possible that they lose some big items. But losing big items are good for them because in the next round, when they are going to choose, they can choose some small cost, which is not available in the ideal instance, right? Okay, so now we go on. We say, okay, since every remaining agent, their remaining bundle, that sequence is actually better than the sequence they face in the ideal instance. Okay, and then for agent 2, right? So next agent 2 will choose 2 items because the order is here, right? 2, 2. So agent 2 will choose what? Agent 2 will choose 1, 1. Okay. Oh, okay. So there's a typo here, right? Sorry, that's indeed a typo. Agent 3, the 2 3s, one of them should be 1. Okay. So this is a typo. Yeah. Very good. Very good. Oh, I didn't realize that such a typo is here. Okay. So now I will correct that after the lecture. Now for agent 2, right? He chose 1 and 1. He's able to choose 1, 1. And you see that actually these 2 values, each of them might be smaller than its corresponding item in the ideal instance, right? So now you see that actually the criteria we have here is not only these 2. The second one, the value one, should be a more strict one. Okay, we should guarantee that the items allocated to the agent in the general instance is piecewise smaller or piecewise equal compared to the ideal instance, right? So if you earlier have 3, 2, 1, now I have 2, 2, 1, that's good, right? So that's the property we want, right? Okay, so you see that agent 2, it got 1 and 1, right? Okay, now again, because agent 2 get 1 and 1, then agent 1 lost 4 and 1. Well, but that's very good because he lost 4. He will no longer face 4. So agent 1 now will be very happy. He can even choose an item with cost 0, right? Because he lost all the heavy items, right? Okay, so now the principle behind is the following. With this picking order, everyone picks an item which is better than before or the same as before. Okay, so you can guarantee, right, the new allocation in the general instance is also a prop X allocation. Okay. Yes, yes. So Winchong, you're right. We are transforming a general instance to an ideal instance, and then there we use some algorithm to find prop X, and then we transform that prop X solution back to the original instance. But this transformation is not kind of transformation. It's only telling you some picking order, right? So in the ideal instance, the item value, you sort it according to their respective agent. And then you say, okay, if somebody gets a small cost item, then it has a higher probability of picking at the beginning, right? Okay, so we use this picking sequence to decide how to allocate items in the original instance. Okay. Well, so I would like to do a very simple survey. Okay, so did you get the idea about how to get an ideal, or get an prop X allocation in the original instance after you have the solution for the ideal instance? Okay, so I will pause the polling for now. So basically, yeah, about three quarters students got the idea. Now, for those who didn't get it, well, no worry. This is a sub procedure, right? So we're just trying to show, if you are able to get a good solution for for the ideal instance, then you can also get a good solution for the original instance, right? So this is the main purpose. Now, the details, you can get it, it's good. Now, if you did not get it 100%, you can still spend some time after class to figure it out, right? But now, let me just answer some questions here. So Ziao asked, yeah. So the remaining question is how to find prop X allocation for ideal instance. And then can you explain one more time on how to allocate for I prime? Oh, okay. Yeah, so actually your questions are all the same, all right? I didn't say anything about how to allocate in I prime because I didn't ever give you any solution, any prop X solution for ideal instance yet, right? I didn't give it to you yet. So no worry. Let's just continue, all right? So for now, all three questions are the same. So we will move forward. So now let's see, for ideal instance, how to get prop X allocation. Well, the good news is we know in ideal instance, top NV cycle elimination algorithm can give you EFX allocation, right? This one we already explained. You just assign the items according to decreasing cost, right? Okay. So now in their paper, they prove the property. They show that any EFX allocation is prop X. So basically, that means what? That means you can use top NV-free cycle elimination algorithm to return a prop X allocation. Okay, so now we have an algorithm to generate prop X allocation for ideal instance, right? So I guess this solves your question, right? Okay, now of course I'm not so I'm not going to explain it in great detail, okay? And then based on this lemma, okay, based on this lemma 2 and this fact, okay, we have theorem 3. Prop X allocation exists for any instance and can be found by top NV-free NV cycle elimination. Okay, so very brief explanation about the so very brief explanation about lemma 2, which is why any EFX is prop X. So I guess this answers Wing Chung's question, right? I'm going to prove some, right? So this is one of the sum. Okay, now for EFX allocation, what does it mean? It means that I remove any item, right, from my bundle. Its cost is less than or equal to other people's bundle, right? And then it's very natural to write down another, even easier one, right? If I remove an item from my bundle, of course, my cost is less than or equal to my cost for the whole bundle, for my whole bundle xi, right? Now with these two, you can expect the next step, right? What's the next step? The next step just add, right? You just add all these equation inequalities. If you add for all the j, then on the left, it will be n copies of ci xi removing e, right? And then on the right, you are adding up all the bundles, right? Xj, xi, etc. It becomes CIM, right? Okay. So what does it mean? Sorry. What does it mean? This is exactly the definition of prop X, right? Okay. So CI xi/e is at most 1 over n times CIM. So that means, well, it's true, right? So EFX, any EFX allocation E can give you the proportion up to X, right? From prop X. Okay, well, that's very easy. Well, although maybe I will not give you such a proof in the final exam. That's just too easy, right? Okay, well, anyway, there will be some other types of proofs, probably. Okay, so now you see, we have a complete solution, right? We have a prop X allocation for ideal instance, which is actually the EFX allocation we generated by top MV3 cycle, top MV cycle elimination algorithm, right? And then it can further give us the solution for the general instance, right? From IBO to general, yeah, it's natural, right? Okay, so basically all the building blocks are here. And then that's the most elegant algorithm I promised you in the last lecture, right? So the picking sequence is indeed very, very intricate, right? So, well, this result is just discovered last year. So it's very, actually it's very unusual because, well, such a simple setting, but it's the truth, right? So that means that sometimes research can also contain simple results. If these simple results can give you, well, indication of interesting results for some popular problems, right? Okay. Now the next question is, we have one algorithm to generate prop X. So can we have easier algorithms? Because, well, top MV cycle elimination, that algorithm is somewhat too complicated. All right. If I ask you to do this thing in the final exam, it will take you quite some time, right? You need to construct graph, and then you need to shift the bundles. You need to further allocate one item to those who do not envy other people, right? So basically, the simulation of the algorithm itself is already quite challenging, right? Okay. Yeah, Jianchong is suggesting something. The person with fewest cost pick the next chore. Yeah, maybe. Actually, we are going to explain two things, and these two things, they are also very interesting. Okay, and Ziya is asking, are most research papers built on this algorithm? Well, you mean, I guess you mean research papers on fair division of chores, right? Not necessarily. Okay, so only one paper, I think, now is using this technique. So fair division actually has quite some different techniques. Not only this one. This one is the one this one is the one I think. Well, people like us, right, normal people can understand, all right, and it can solve some important problems. Now there are also other techniques, but maybe some other techniques, some of them will be too challenging to understand within a short time. But this one definitely is one of them, one of the questions which does not require sophisticated math or other knowledge, right? Okay. Well, so now let's move on to the next two algorithms. Let's look at one very simple algorithm. So what's this algorithm? This algorithm is following. So, okay, we still sort all the items according to decreasing cost. And then we try to ask each agent to report their proportional cutting point. So what does it mean? It means that if I treat all the items as uniform within the item, so one item has a cost, C, for example, this item has some cost, right? And then we treat it as a uniform. So if I cut it into half, then it will be half cost. All right. So basically, now each person will tell the algorithm, okay, where is my proportional share? Okay. Second person says, okay, if you give me so many items, it will reach my 1 over n proportion. Right. And agent 3 says, okay, if you give me 2 items together with part of item 3, I am reaching the 1 over n, right, sum. Okay, so each person has some kind of reporting, right? Okay, and then the algorithm says, okay, since agent 3, you are, well, you are the most flexible person, right? So because your proportional share is quite far away from others. You can, if I if I give you this piece, other people will be very happy because they will get rid of more than proportional share of items, right? Because their actual proportional is earlier. So it's just like in cake cutting, remember? Everybody can shout, okay? Now, please stop. You already reached my proportional. But remember in the cake cutting scenario, yeah, moving knife, very good, okay? So it's a moving knife protocol, right? In cake cutting, because it's dividing cake, dividing goods, right? So the first one who shout will get that piece, right? Because everybody else lost less than proportional. That's good. But now we are talking about chores, right? So we are talking about chores. So that means, okay, we should well, give the cake or give the chore cake to the one who shout latest, like Jiantong said, right? Okay, so who shouts latest, I will give the bundle to that person. Okay, so this way I will give away a chore which is more than proportional for other people, right? But right on proportional for this person. Okay, so this is the algorithm. Very easy. I just allocate these items to agent 3. Now here we are using roundup. Okay, the reason we can use roundup because we are not talking about proportional. We are talking about proportional what? X, right? Okay. All right. And Yuqi said that piece 2 may be very cheap for agent A. That's right. Piece 2 can be very cheap for agent A. That's fine, but still agent 1, right? Agent 1, its proportional is in the middle of item 2. So still, if I give 3 items to agent 3, 1 and 2 will not be unhappy, right? So let's see some calculation, right? You see that in terms of C1, right, cost 1, agent 1, he thinks this piece agent 3 gets is more than his proportional. And agent 2 also thinks what agent 3 gets is more than his proportional, right? Okay, so basically they get rid of some part which is more than proportional. That's good for them. And for agent 3, after removing the last item, he is pretty happy, right? Okay, because we are talking about X, so I can remove this item. So removing this item, agent 3 will say, oh, good, right? I only get 2 items, which is less than my proportional cost. That's good. So all 3 people are happy, right? Agent 3 is happy because after removing one item, he's happy. And then agent 1 and 2, they get rid of more cost, right? They're also happy because the remaining cake, let's see, for any agent 1 or 2, the remaining cake is less than 2 times his proportional, right? And then the whole process continues, right? Because now 2 persons are dividing a chore into 2 parts, right? And each of them try to get only a cost at most proportional, at most it's proportional, right? At most this value. Okay. Well, so next step, they report again. Agent 1, agent 2 says, okay, now here is my cutting point. And then I will allocate the 4 items to agent 2. Okay. And then the remaining piece will be very cheap for agent 1 because this piece again is more than proportional share of agent 1, right? Okay, so he gets rid of 2 pieces which have higher cost than his own proportional. Therefore, the remaining one must be less than his proportional, right? Okay, so you see, well, that's good, right? I will just conclude here. All right, by using this moving knife, but now we are dealing with chores, right? This moving knife can give you proportional up to any item allocation. And this algorithm actually is much simpler compared to top NV cycle elimination, right? Okay, now we'll continue with the third algorithm, and then we'll take a break. Now the third algorithm, it has some consideration about some point some of you raised earlier. You say, okay, some item may be very cheap for some person. You give it to another person who values it, whose cost towards this item is more. For example, agent 1, 2, 3, right? There is one piece of item. Suppose this piece, right? This piece of item, it may be only values 0.1 to agent 1, okay? But it values 1 to agent 2, and values 2 to agent 3. And then very naturally, you will think, okay, this item probably I should give to agent 1 instead, right? I'm going to give to agent 1. Why do I give it to agent 2 or 3? That seems a waste, right? So now this algorithm is dealing with this drawback. Okay, so let's see how to do it. The first item, I give it to some agent whose cost towards this item is smallest. Okay, all right. And then second item, again, I give it to someone who values it least. Okay. And then third item, same. And then I continue. Okay, continue. Until at some moment, somebody gets more than proportional. Then I stop. I will get rid of this agent. Okay, because he already gets more than proportional. I cannot give him more. Right? That's not allowed. Okay, so at this moment, you see, agent 2 got a bundle at least 1/3. Okay, and then agent 1 and 3, they get rid of some item. Because remember, when we allocate items, we allocate to the agent whose cost towards the item is smallest. So that means agent 1 and 3, their cost of these items are higher than agent 2's cost towards these items, right? So since agent 2 thinks he gets more than 1/3, then of course agent 1 and agent 3 will also think, these items is worth, or is their cost is far above 1/3, right? It's above 1/3 definitely, because, well, to agent 1 and 3, these items has higher cost compared to towards agent 2, right? Okay, so now agent 2 says, oh, do not give me any more, I'm already 1/3. So agent 1 and 3 said, of course, now this bundle is very, very good to be thrown away, because we also think this bundle is higher than 1/3, right? Okay, yeah, so this is the philosophy of the third algorithm. And this algorithm, we call it bid and take. So you order the items in some order, right? And then each person says, okay, I think the cost is this much. You think the cost is that much. So eventually the item will be given to the agent who bids lowest. So, okay, my cost is lowest, I get the item, right? Okay, clear about the algorithm? So this one is proportional up to x. And also it's very easy to prove using the same philosophy. Okay, so we'll take 5 minutes break and then come back. Okay, so during the break, I may answer some midterm related questions, right? So midterm related questions. First question. Oh no. First question is about average score. All right. So the average score is 47, higher than we expected in the last lecture, right? Because in the last lecture we say that probably is around 40, but it's close to 50. And then highest score. Good question. I need to check the canvas. I remember it's 86. Let me see. Yeah. Highest score is 86. I have a good memory. And assignment 2 and in-class exercise 1. Let me check the status. Assignment. So assignment 2, the average score is 88, which is very high. Okay. And then in class, I guess it's less important, but still just let me tell you the grade. In class exercise 1, the average is 4.77 over 5, which is also very high. Okay, it's close to 5. As I said, I will not ask a TA to mark this very rigorously, just to check the general feeling of the questions. Okay, but I do check the questions raised in class very seriously. Okay, so any other question? Sorting criteria current algorithm. Okay, very good. Okay, so Yuchi asked about the sorting criteria of the current algorithm. Actually, what do you think? Now, what do you think? Do you think it should be sorted or not? It's a very good question. Remember that we are talking about ideal instance earlier, right? So for ideal instance, well, of course, you can sort according to this, right? Right? Item 1 is the heaviest, item 2 is the next, and then next, right? You can sort according to this. But actually, this algorithm, oh, okay. Yeah, very good. Very good. So the reason we sort this ideal instance in this way is that we try to make sure the last item is the cheapest. Yeah, so very good point. So that's also why this algorithm, if you talk about prop X, okay, not prop 1, if it's prop X, then very likely it can only work for ideal instance when you sort according to decreasing cost. Yeah, right. Yeah, so all the prop X algorithm we talk about is for ideal. But another thing which I would like to say is, if it's general instance, then this algorithm is also good for prop 1, right? Because prop 1, you can remove any item. Well, you can remove some item you want. So if it's general instance, then prop 1 is very easily obtained, even if you do not sort anything, right? Okay, yeah, very good point. And now we'll continue. Okay, so let me write down something first. Okay. Now the next one we are going to talk about is another interesting fairness measure. Earlier we have two major fairness measures. One is MV-free. Second one is proportion. So now the next one, equally important one, is called max min share. What is this? Let us see why we have this kind of max min share concept. Firstly, let's look at proportional. So we know that proportional means the cost obtained by agent I is at most 1 over n, the average of its overall cost, right? Now, but now let's imagine something. It says, okay, suppose we adopt the cake cutting scenario where one person cut and then other people choose. So let's just extend this two-person game into multiple-person games. Okay, you have n people now, and then the first person will cut the cake. Okay, cut the or divide the bundles, and then the remaining people will choose. How they chose, I don't care. All right, but I need to prepare for the worst scenario. The worst scenario is after all of them choose, the first person is left with a bundle which is worse for him. Okay, just like cake cutting, right? In the cake cutting, you said the first person cut in 2 pieces, the second person take 1 piece, and the first person take the other. So the first person has to make sure that he cuts very equally, right? In case he was left with a smaller one, he will be very unhappy, right? So he would try to make the smaller one as big as possible. The best he can do is to make the 2 pieces equal, right? But cake cutting is divisible goods, right? You can divide arbitrarily. But now we are talking about indivisible chores. So basically, when you divide, you cannot expect to divide the bundle into equally important shares, right? Okay, so now this agent, he would try to divide all the items into n bundles such that the smallest bundle, the largest bundle is as small as possible, because we are talking about chores, right? We hope that in the worst case, he will get a bundle which is not too bad. Is it okay? So then, you see, well, no matter which partition he gives you, right? Gives you, the largest one is at least the average. The average is what? Average is proportional share, right? Okay, so basically, no matter what he did, right? So eventually, well, if you adopt this process, ask him to divide, and other people choose, and then he was left with 1 bundle, and this bundle very likely will be the worst one for him, and then this one will be definitely higher than proportional. So if we want to relax proportional concept to this value, then probably we can do better, right? So we can get some kind of better guarantees for the algorithm's performance. Okay, now, so the reason we introduce this relaxation is that proportional allocation may not exist, right? Just now we only talk about proportional 1 up to 1 or proportional up to any item. So these two, they will exist in indivisible goods case, but proportional, well, very unlikely, right? So we are trying to relax the proportional concept to the so-called max-min. What is this? Okay, so here is the official definition. Max-min share of an agent. Okay, yeah, you are right. It should be min-max. Okay, I'm still stuck in the goods case. In the goods setting, it's max-min, right? Maximum the minimum bundle. But now it should really be min-max. Okay, so these two M's, now they switch their roles. Okay, it becomes min-max. Okay, but because this concept is proposed for goods first and then come to chores, so people would like to still call it max-min share. So min means worst. Okay, we try to maximize the worst bundle, or we try to make the worst bundle as good as possible, right? In the chores case, we are trying to make the largest cost as small as possible. Okay, so you see that the official definition of max-min share is the following: over all the division into n bundles, we take the cost of the largest bundle, okay, and we try to make that cost as small as possible over all the possible divisions. Okay, now this value will be different for each person. Okay, proportional value is the same for each person if you do normalization, right? So if everyone's cost towards all items, they add up to 1, then with this normalization, everyone's proportional value is the same, but everybody's max-min share value is different because they have different views towards the items. So when they divide, the best they can achieve is also different. Okay, so yeah, again, as usual, I would like to ask whether you understand the concept of max-min share. What does the value mean? Yes or no? So you try to, for each agent, all right, he will divide the bundles according to his own view. he tried to divide it into n bundles such that the worst bundle has the smallest cost. And that division, that smallest cost, the worst bundle's smallest cost, is defined to be max min share value of that agent. Okay? Yeah, okay. Now, I guess I will end the poll, and then maybe I just explain one results to see whether you know what it means. Okay, so suppose I have two people. Okay, I have the first agent is 7532. Okay, this is the first person. 7532, 4 items. What is his max min share? Yeah, so it should be 9, 7, 2 together, 5, 3 together. This is the best he can achieve. One bundle is 9, one bundle is 8. So 9 is the bottleneck, right? So 9 is the worst he will get for this division. So 9 is bottleneck. Can it be even smaller? Well, if you want it even smaller, it should be 8.5, 8.5. But that's not possible because all of the numbers are integers here, right? So 8.5, the very equal cut, is not possible. So 9 is best. If you can find one 9, you're done, right? Okay, so that's the max min share for this agent, right? With the value 7532 towards all the items when you have two people, of course, right? When you have two people. Okay, so Ziao is asking a very interesting question. So this max min share value, you don't need to know other people's valuation, okay? You just divide it according to your own knowledge about the items. Yeah. If you know other people's value, then you can manipulate. You say, okay, if I do this way, then after they take away their most preferred bundles, I will be better off. That's totally likely, right? Just like cake cutting, right? Cake cutting, the first person who cut the cake, well, if he knows the second person's value, then he will not cut into half. He will cut in a way that the second person will get half of his value, and I will get more than half, right? So remember that when we talk about whether people will be honest, remember? So if in the cake cutting setting, one agent knows the other one's valuation, he will not be honest for sure. Okay, he can manipulate. It's a very good point. Okay, so max min share, as I said, everyone has different max min share value, and then we say an allocation is MMS fair if for any agent his cost is at most his own max min share value. Okay. Now we know for indivisible goods, proportional allocation may not exist, but sometimes max min share or max MMS fair allocation does exist. Okay. And then, well, in general, bad news first. Okay. In general, MMS fair allocation also do not exist. Okay. Well, how to show MMS allocation does not exist? Well, you just need to create an instance and then just enumerate all the possible divisions, right? And then to try to show no matter which division, how you allocate to different people, they all exceed their MMS value, right? At least one of them, right? At least one agent, his MMS value is exceeded. Then it's some kind of non-existence results, right? And then, since, well, MMS also does not quite exist, then people say, oh, how about we relax it? We say we want approximate MMS fair allocation. So we introduce this alpha coefficient. We say, okay, now everybody's cost can be at most alpha times its MMS value. And this alpha is larger than 1. Okay? So basically, I can tolerate more, right? Originally, I said, okay, I only suffer 9, but now it's 9 times 1.2. I can allow for some kind of 10, right? Up to 10. So this is the relaxation of MMS. So you see that here, approximation is also somehow incorporated into the setting of fairness measure, right? Okay, and then in the recent paper, they show that a prop X allocation is always 2 MMS. Okay, it's 2 approximation of MMS. And then the other direction is very bad. An MMS allocation can be very bad. It can be theta n prop X. Wow, this is quite amazing. It's a huge difference in the two directions. Okay, and then with the result earlier, then you can see that actually the 3 algorithms we did discussed previously, because they return prop X allocation, then very naturally they guarantee 2 MMS allocation, right? And then in the 2017 paper, they showed that round robin algorithm can return 2 minus 1 over n MMS allocation. And then actually, well, for top NV cycle elimination algorithm, it can give a better than 2 approximation. It can give a 4 over 3 approximation. That's better, right? Now, can we improve this? Well, the answer is yes. So recently, there's one paper improving the ratio to 11 over 9. Okay. Now here, I'm only going to introduce high-level idea. These are very research-oriented, so I will only briefly introduce the results. Okay. Now, remember that famous lemma. Say, okay, if for ideal instance we can get a prop X allocation, then we can also get a prop X allocation for general instance, right? And we have similar thing called, if you can get a alpha approximate MMS allocation for ideal instance, then you can design a similar algorithm for general instance. Okay, so again, it's on ideal. And remember that we have a moving knife algorithm, right? So the main difference between this one and the moving knife is the following. Moving knife says what? Moving knife says that the items are allocated to each agent. They're somehow contiguous. They're together, right? In the same range. They are together into one block, right? So basically, you say you can imagine this moving knife to be really moving. So I move to the first item. I ask different people, are you okay? And then if somebody said, I'm not yet reaching my boundary, okay, then I continue, right? Allocating the second item and then third item. Now I will do it until somebody, all the people say, okay, we are done for the first piece. And then you give the whole bundle to the agent who shout last. Okay, but you see, well, there is one thing, right? So the one thing is, if some item makes all the agent not happy, then maybe we can skip it. Okay, so you see that when I move it, right, move to this one, say okay, the back will immediately stop, right, and then you allocate all the 4 items to one person. Well, so they suggest that probably we can skip this item. Okay, try to see whether by allocating first one, second one, third. Oh, so I can put some items into the bag according to the order, and then if some item putting into the bag makes the whole thing bad, I will skip this item and then allocate the next item to the bag. So I would do it in such a way that this bag may potentially contain more items, and then it may make the overall fairness measure good. Okay, so you see that probably the bundle looks like the bag looks like this, right? First bag. Now, but the problem is, if you do this, then some items will not be allocated, right? So they will be somehow not handled in the end of the algorithm. That's why they need to relax this MMS to alpha times MMS, such that they can guarantee all the items will be allocated. Okay. Now, as I said, this is only a high-level introduction. You do not need to know the details. And then actually, this alpha in that paper, they show that alpha equal to 11 over 9 will be sufficient to prove the ratio. to prove that all the items are allocated. Okay, but still, this 1109 is not tight. People can still continue to close the gap. Okay, so up to now, we have finished the core part of this chore division. Okay, now we come to some other considerations that you may have for this kind of dividing chores. Now, one thing is there's some difference about the reported value. Right? Now we have two words. One is called cardinal. The other is ordinal. So cardinal means I know the exact values of cost for different agents. Ordinal means I only know the order. All right? I only know that agent 1, he hates item 1 most and likes item 6 most. I only know this kind of order. All right? So for ordinal valuations, then we call it partial information because we do not know the exact cost value, right? Okay, these values are there, but we don't know. So when that happens, we may still go for some approximation, right? Say, okay, if I don't know the value, I only know the order, how well can I do in terms of if I compare with optimal solution? Okay, now different algorithms we introduced earlier, they will be friendly to different valuations. For example, if you want to do MV cycle elimination or moving knife, bid and take, they all need to use the cardinal valuation. They need to use the exact value of C. Otherwise, they cannot work, right? Now, for round robin, okay, this one is good. This round robin says everyone take turns to pick items, right? So when you pick items, I don't need you to tell me this item's cost is 10. I don't need you to tell me this. You just pick the smallest cost one, and that's it, right? So basically, round robin algorithm, they only need the order value, right? So round robin is an algorithm friendly to ordinal valuation, right? Okay. Now, with only order, sometimes you cannot get the optimal solution. So let's look at one example. You see here we have an ideal instance, right? On an ideal instance, 4 items and 2 people. And then say, okay, any cardinal value will be okay if they're consistent with the ranking. So let's see how good can we do for allocating these items. Now, in your allocation, you know that item 1 has to be assigned to one agent, right? So which agent is item 1 assigned? Well, suppose item 1 is assigned to agent 1, okay? So because now I didn't tell you any, because now agent 1 and agent 2, they are just symmetric, right? It's IDO, so I basically cannot differentiate which one can contribute more to the optimal solution, which one is less. So basically, this abbreviation is without loss of generality. We can assume item 1 is allocated to agent 1, and then let's divide into several cases. Suppose agent 1 only receives this item, then we can design the actual cost in the following way for agent 2. So, okay, agent 2 thinks these 4 are the same. All of them are 1. Now, what is the maximum share of agent 2? Easy, right? Maximum share of agent 2 is just 2, 2, right? Dividing 2, and then each group is 2. So maximum share is 2. But how much does agent 2 receive? You see, agent 1 only gets 1 item, right? Only gets the first item. So agent 2 will receive what? The remaining 3 items, right? Okay, so actually, agent 2 receives a bundle whose cost is 3, but his ideal cost is 2. So it's kind of 3 over 2, right? You can never do better than 3 over 2 approximation, right? Okay, any question about this argument? I guess this is okay, right? Yeah. Now we'll continue if I didn't see questions. All right. Now, just now we say if agent 1 only receives 1 item. Right? Now, how about if agent 1 receives 2 items? All right. And then we will design agent 1's cost to be 3111. It's also consistent with the ordering, right? Okay. Let's see. Okay. Now, agent 1 receives what? Agent 1 receives a cost of 4, right? cost of 4. But what is this max min share? Max min share is this: 3 in one bundle and 111 in one bundle, right? So it has a perfect split, 3 and 3. So max min share is 3, right? So that means, okay, your actual cost is 4, but your max min share is 3. So the ratio, the approximation ratio is 4/3, right? Okay, so you cannot do better than 4/3. Well, so you see, this example tells you what? It tells you, actually, if you only know the order information, then you cannot do better than 4/3 approximation for MMS, right? Because no matter, right, how many items you allocate to agent 1, well, somebody will get a cost which is higher than a certain ratio times the optimal MMS, right? His MMS value. Okay, so then maybe some of you may ask me, oh, why you do not discuss about if agent 1 receives 3 items? Why? We should also discuss that, right? Why I did not say that? Or 4 items, maybe. If you want to be logically correct, you should somehow be complete, right? It's not symmetric. It's not symmetric. Okay. I didn't see the answer yet. It's not symmetric. Why I do not discuss that agent 1 gets 3 items? Item 1, item 2. Okay, I mean, I guess I get your point. Okay. So you are saying that 2, 3, 1, 2, 3, 4, they are symmetric. They can be considered as symmetric in the example we constructed, right? In the example we constructed, we can say, agent 1 gets item 1 and item 2, item 1 and item 3, item 1 and item 4, right? Okay. Well, but how about if agent 1 gets 3 items? Item 1, item 2, item 3. It may also happen, right? But then 3 items, the ratio will be so Jianchong said it is. Yeah, so that's the point, right? We should discuss about 3 items and 4 items, but they will be very bad in ratio, right? Even if you only get 2 items, your ratio is already as bad as 4/3. So if I give you 3 items, it will be even worse, right? But they may happen because I did not exclude this kind of possibility, right? Okay, so well, as a rigorous proof, you should make the whole thing complete, right? So that's my point. Yeah. So basically, I know that many of you know that it's somehow like this, right? But to make the whole thing rigorous, we do need to cover those seemingly very bad case, but we still need to say it, right? And then Jianchong is asking me, MMS2 equal to 3. So actually, here we are not talking about identical valuation. So MMS2 equal to 3 does not mean MMS1 equal to 3, because they may have different realization of costs. So it may not be the same. It may not be the same. Yeah, it may not be the same. Okay. Yeah. So remember, if you have cardinal valuation, we have 11/9 MMS allocation, right? But when you become ordinal, your value is worse, right? Your value is worse. It's 1.33, but this one is only 1.2 something, right? Okay, so you are losing something. You are losing some factor of approximation ratio if you cannot know the exact costs, just the order. All right, if you only know the order, then you cannot achieve that good things, right? Okay. Now, this one, 4 over 3, it tells you the gap between the cardinal and ordinal preference, cardinal and ordinal valuations. Okay, so now comes to another important point. Again, here, we try to design some algorithm which is good for ordinal preference. Okay, and then just now we say if you have 2 people, we already show that you cannot do better than 4 over 3, right? And in their paper, they show that if you have 3 people, you cannot do better than 1.4. You have larger than or equal to 4 people, you cannot do better than this. So these are called lower bounds, right? No algorithm can achieve a ratio better than these, right? This basically marks the limit your algorithm can go. Now, with this lower bounds, of course, people would think, is it possible that we can really design some algorithm that can generate solutions with approximation ratio exactly that value? For example, for 2 people, can we achieve that 4 over 3 by designing an algorithm? Well, that would be very interesting, right? Okay, so the answer is almost yes. Okay, so let's see. How about round robin? Let's first see round robin performance. What is round robin here? The round robin says you repeatedly pick items, right? Okay, and then you see item, right? We have 6 items. Now again, we are talking about the ideal instance, all right? So they will pick alternatively A2 pick first, and we force them to pick the larger cost first. Okay, so we force A2 to pick the largest one, and then A1 to pick the next one, and then A2 to pick the next one, A1 pick the next one, A2, A1, okay, in this way, right? Or in other words, you can also imagine if I do not force you to pick, then I will reverse the picking order. I will ask A1 to pick first, then he will pick the smallest cost, and then A2 pick, right? And then A1 pick, A2 pick, A1 pick, A2 pick. So this is round robin, right? But this round robin, definitely somebody has advantage, right? So as we can see, A1 has an advantage because every round he picks a smaller cost one. So he has more advantage. That's not fair, right? So maybe we can do the following. We say, because A1 picked first, I will ask you to pick 2 items, right? And then followed by A2 picking 1 item. And then I'll ask A1 to pick another 2 items. And then A2 pick the last item. Will this be good? Okay, so in other words, we want this. Okay, well, that's interesting. So we ask the one who picked first to pick more, right? And then the one who will pick later to pick less. Because the one who picks later will pick a larger cost one, so make it pick less, it will be good, right? Okay, so in their paper, they show that if you have this picking order, it will give you 4 over 3 MMS allocation. Okay, so I think that this should be 112, should be 112, or maybe, well, it's kind of if you treat it from the left to right, it is 122. Okay, second person will pick. So 122, 122 means player 2 pick 2 items first, and then player 1 pick 1 item, and then player 2 pick 2 items, player 1 pick 1 item. So this can achieve the lower bound, right? 4 over 3 approximation. That's very nice, right? Okay. And then they further showed that 1, 2, 3, 3, 2. This picking sequence will give you 7 over 5 MMS allocation for n equal to 3. This is also tight, right? It also matches the lower bound. Okay, and then they further have this one for n players, and it can return 5/3 MMS allocation. But this value is larger than the lower bound. Okay, so there's a gap between these two bounds. Okay. Well, so now let's just do a very brief exercise. 1, 2, 2 give you 4/3 MMS allocation. Why is that? For example, I use this one, right? 1, 2, 2, 1, 2, 2. Okay. So how to show this? Now I would leave this one as an exercise. Probably if we have time after we explain the midterm paper, we'll come to that. Okay, this 4/3 proof is not difficult. Okay, I believe that many of you can figure out the solution well easily. Okay, well, I didn't announce that to be in class exercise yet. Okay, so I mean that probably we'll go through it sometime today or sometime next week about this 4/3, but I will encourage you to think about it first. Okay, before I explain, I would encourage you to think about it, but you don't need to write it in class exercise. Okay, so I would say that it's good to understand the reason of choosing those picking sequences, why you choose these sequences, why they can get good ratios. And then for the fair division topic, in the final exam, I'm not going to test you goods. I'm only going to test you on chores. And then the two main part is about the picking sequence. Okay, so remember that today we explained two picking sequences. One is for transforming the solution for ideal instance to the solution for general instance, right? The second picking sequence is this one. All right, you choose the picking sequence of agents such that, well, after agents picked, the final allocation will be a certain kind of MMS approximation. Okay, so these two parts will be in the final exam. For the other part, they will not be there. Okay. Well, so you can see that closing the gap for n larger than or equal to 4 is an open question, right? And you can also see that for 2 and 3, they are really elegant, right? They match the lower bound, and the picking sequence itself is not difficult, right? And also it's kind of expected. Why? Because, well, for example, for the case of 2 people, you would imagine that for people who pick first, you should ask them to pick more items, right? Okay, so the next Ying Chung is asking, we should be able to find the approximation of some sequence. Yeah, you're right. You should be able to find the approximation of some sequence, and furthermore, you may be asked to design some sequence which have good approximation ratio. So all these will possibly appear. And then, so then I move on to the other considerations. Now, one other consideration is strategy proof. And this concept will also be used a lot in next week's lecture. Okay, strategy proof, actually, Taiki already told you, it means that people will not lie, right? If they lie, they cannot get more. Okay, so that's the basic idea. And here, it's the same story. If we know nothing about agent's preference, even ordinal valuation we do not know, then how to incentivize agents to tell you the truth, right? Okay, now here, we need to design mechanisms. All right, we try to say, I designed the algorithm mechanism in this way, and then people following this protocol, they have no incentive to cheat about their valuations. Okay, or in other words, reporting the true valuations will be the dominant strategy. Okay, and then let's see, how about round robin? Is it good? We have a following table. We have 3 items, 2 agents, and then round robin says one pick, agent 1 pick first, right? Okay, he pick item with the smallest cost, right? And the agent 2 pick, he also picks the item with smallest cost. And then agent 1 pick again, he pick item, last item. Okay, is this good? We can see that, well, agent 1 says, maybe I should not do this. Okay, yeah, so A1 actually can pick second item. It says, okay, I misreport. I said that second item is the cheapest. I pick second one first. After I pick this one, agent 2, without the possibility of choosing the second item, you only choose this one. And then you see agent 1 is very happy. You got the item with cost free for me. That's nice. Then I can get item with cost 2. So by cheating his cost towards the second item, he wins, right? He can get a less cost compared to telling the truth. So that's not good. Round robin is not good because agent can force other agents to take some item which he really does not like, right? And then, well, the manipulating agent will gain, right? Okay. So you see that this is the result after misreporting, right? Now, from this example, we can learn some lesson. See, okay, if an agent has more than one chance to pick items, then very likely he will cheat, right? The round robin, you see, agent 1 picks first, and then agent 2, and then agent 1. So agent 1 has a second chance to pick. So that's not good. In order to be strategy proof, you have to ask each agent to pick only once for multiple items. So here, they design an algorithm called consecutive picking algorithm. Again, you need to fix a sequence of integers, right? It means what? It means that, for example, agent 1 pick first, and then agent 2, and then agent 3. I only let them pick once. And then agent 1, when you pick, I will tell you how many items you should pick. So here, I'm saying, pick K1 items. And agent 2, when it's your turn, you pick K2 items, and so on, right? Okay, now you see that the one who picked first, you should somehow ask him to pick more, right? Okay, so that's why we need to guarantee K1 is at least K2 is at, and K2 is more than K3 is at, and so on, so right? Okay, and then you may have a further, more refined condition saying that Ki over Mi is the remaining items. It should be less than or equal to alpha over n if you want to achieve alpha approximation. But I'm not going to talk about details here. Okay. Now in the theorem, in their paper, they show that the optimal approximation ratio guaranteed by this consecutive picking algorithms is big O of log m over n. M is number of items, n is number of agents, right? Okay, well, it's not too good. It's not very good because it's logarithmic, right? Okay, now there's one open problem. Can we have a better ratio, right? Can we have a better approximation ratio? Now, so the problem is actually we do not know how to use the cardinal information in a strategy proof way. Okay, with the cost, with the actual value, probably know, but if you only have the order, it's very difficult to use. So that's increase the difficulty of the whole problem. And then if you further allow randomization, remember we talked about randomized algorithm, right? So for mechanisms, there is also randomized mechanism. Okay, so here it says there's a randomized algorithm that is strategy proof and also achieve a square root of log n approximation. You see, this one is better than, in some sense better, right, than log m over n. And this approximation is in expectation. Now, in the next lecture, we are going to talk about the difference between randomized algorithms, okay, because for the strategy proofness in randomized algorithms, they have there are two different definitions. Okay. And now you can also consider the so-called asymmetric agents. Up to now, what we talk about are all symmetric. So symmetric means what? Symmetric means everyone is the same, is equal. Okay, equal means no difference. Everybody is on the same position. Okay, it's not that somebody is more important, somebody is less important. There's no such thing. But we can apply such thing. So in other words, when we can assign some weights to different agents so that that agent will receive a certain proportion of the items, not the same anymore. So originally, proportional says 1 over n, right? It's 1 over n, right? But now it's 1 over n, 1 over n. We can say that agent 1 will get half, agent 2 and agent 3 get 1/4, right? We can do this things like this. And then we will allocate items according to their shares. Now, we say allocation is weighted proportional if its cost is less than its share. Okay, so this is a generalization, right? It's generalization of equal share. And then you can define those prop x things very similarly. I'm not going into details. They are just straightforward extensions. Okay, prop 1, prop x, right? And then again, that lemma can be used to deal with the prop x or alpha approximate MMS for this case, and also can apply for weighted props and so on. Okay, so let's use one example to explain. So bid and take algorithm. Bid and take means for one item, it will be assigned to somebody who values who thinks its cost is smallest, right? Okay, well, this can still be done, right? You can just keep assigning until somebody exceeds a certain threshold. Now earlier it's 1 over n, right? But now we can do what? Now we can say, whenever you are more than 1 si, I stop, right? So it's very similar. All these algorithms, they extend naturally, right? So the bid and take one extend naturally to the case for asymmetric agents, agents with weights, right? Okay, now, yeah, so I will omit these details. And then you can also define the so-called weighted EF1. What is the weighted EF1? Well, so weighted EF1 means the overall cost. I cannot compare cost directly because you no longer have equal share, right? If you equal share, I can say my cost is less than your cost because we are equal. But now we have different shares, so I need to divide by share before I compare, right? So I say, okay, my cost divided by my share, and my cost towards the other bundle divided by that person's share, and this inequality holds, right? So that just means that when you compare cost, remember to divide by share. Okay. Again, these are very straightforward extensions, right? Okay, so I will also omit the details. And then you can also define the weighted MMS similarly, right? So again, when you define the cost, you need to divide by share, right? Okay, so again, it's very easy, right? And then after you, so this is divide by share. This is the definition of the max min share. But because now you have a share, so you have a weighted max min share, you need to multiply this Si on top of this Fi. Okay, and then relaxation is still similar. You can just multiply a factor of alpha, right? Okay. Yeah, here, well, constant approximation is unknown for this version. Okay, so there are also some other fairness measure, but I will not going to talk about them in detail. Now, there are also some further directions. For example, you may consider whether it is possible to have a solution which is both fair and efficient. Okay, so efficient means what? Efficient, it can be socially optimal or Pareto optimal. Okay, Pareto optimal means no other solution can improve in one agent's cost while does not hurt other agents, right? So that's similar as a Pareto optimality concept we explained earlier, right? And then you may also consider social welfare, right? Maximize the social welfare, or minimize the social cost. Okay, so these are also the possible considerations. And then you may also consider price of fairness. Okay, so now bonus question. What do you think price of fairness is? Yes, similar to price of anarchy. So how are you going to define it? Oh, okay, very good. Um, so well, we are not doing subtraction. Okay, so usually price of fairness or price of something, it will be some kind of division. Okay, it will be the cost obtained by a fair solution divided by the optimal solution without the consideration of fairness. So basically, it tells you how much you will lose in order to guarantee fairness. Okay, because well, if you do not consider about fairness, then it's just global optimal, right? And then say, okay, I want to guarantee some fairness, and then you cannot adopt the optimal solution. You have to squeeze down the solution scope, and the overall cost may be bigger compared to optimal solution, but it's fair, right? So it's a total. So as Xuezhen said, right? So it's a cost over optimal, but in order to be more concrete, it's kind of what Jiantong said: total of cost of fair solution over optimal social cost, right? Okay, so this is the price of fairness. But I guess Xuezhen already give the right direction. So okay, so there are also some other constraint settings. For example, there could be some cardinality constraint, okay, or matroid constraint. So basically, it's something like when you allocate items to different agents, right? So these items, they have some constraint. You cannot say allocate item 1, 2, 3 to agent 1. Maybe they are not compatible. Okay, you can only allocate 1, 3 or 1, 2 to agent 1. Not very likely. So this is one type of constraint. And also, cardinality means, well, maybe there one agent can only get 4 items. You cannot give him 5 items. Okay, so there are some kind of cardinality constraint. Well, these constraints, they are very natural. And then also there are some kind of knapsack constraints. Okay, so it has a similar flavor of what I explained just now. Okay, so I guess I will just stop for this version, for this topic. And then I guess that we will make a brief start after I explain today midterm solution, because very likely we have time left. So we will start the topic of facilitation a bit, and then we'll continue next week. Now let's take 10 minutes. Oh, well, sorry, 5 minutes break, and then we come back to the explanation of midterm. And also, I would like to tell you the scope of the final exam. Okay, so yeah, 5 minutes break. Take some water. Smallest bit stands for smallest proportion for the agent. Smallest bit does not mean smallest proportion for agent. Smallest bit just means smallest bit in its own sense. So yeah, absolute value. Yeah, because share is only used when you try to compare the cost. Okay, because all the earlier S yeah, so this S is never reflected in the computation of cost. This S is some parameter given for every agent. Okay, their cost is just their cost. This S says how important they are. Okay, how much they are supposed to get. Page P79, second. Second and MSB is one. Oh, yes. Thank you. And I remember there's a typo here. This one, I guess it's Maybe it's better to change this. I guess I cannot change it because this one seems there are questions. Is assignment 3 going to do 2 weeks later? Yeah. So I will explain something about assignment 3. Because assignment 3 is a paper reading assignment. And then the second topic actually will be officially covered next week. So I think it's a bit unfair for you to only complete it within 2 weeks. That's why the deadline for assignment 3 will be April 21st, which means 3 weeks. Okay, so I probably need to change the earlier announcement, but just use the system time as the right time for assignment deadline. And forbidden take. Forbidden take algorithm. Remember, let me see. Now I think that very it depends on the implementation. Usually we'll do normalization before we do the bid and take. But if you do not do normalization, if you do not do normalization, I don't know whether there will be some problem. Maybe not. So in the example 0.9, 0.2, 0.1, and then 987, indeed the first agent will get first item. And then actually that selection does not make the problem worse because we are talking about prop X. So basically this item can be gone, right? When you compute whether the solution is good or not. It should be okay. And there's another question about second half in-class exercise due time. And that due time will very likely be week 14, the end of week 14. And for someone who didn't arrive, yeah, so this one's already answered. Yeah, Shujun, I guess you're right. If you do normalization. Anyway, you can dig deeper about this process for sure. Yeah, it's our week 14. Okay, do you remember our exam is in our week 15? So the due time will be before the exam for sure. So it's actual. I don't know how to say about our and actual. Okay, so it's the CTU week 14. Okay, not our course. Uh, CTU week 14. Okay. Now I will explain the solutions. Let me share this. Okay. So midterm questions, we'll explain them one by one. Actually, some of them are too easy. I will not explain. Now, first one is about amortized analysis. The amortized analysis, you know that, well, we have three questions here. And first question, so the problem says we can do insert and delete. But whenever your insert makes the whole array full, you will double the array size and copy every item in it to the new array. Okay, so basically some insertion will be very expensive because that will trigger the expansion, right? Doubling of the array. So that's why first question, what is the worst case running time for insert? It should be OM, all right? Because that may trigger the expansion. And then what is amortized running time for a sequence of insert and delete operation? Now this one should be O1. And then, yeah, answering O1 correct will be easy, but proof may not be that easy. Some of you have some general or rough idea, rough direction, okay? So if you have rough direction, okay, you'll get 2 points for this question. If you yeah. So question 1.2 is for n deletion insertion. It's also O1. Okay, I will explain why very soon. Okay. Now the proof, I think that well, an easy way to do the proof is by some kind of credits, right? So like what we explained in the lecture, you give credits to some operation. But remember, this time, if you delete, you will also need to give credits. I think I didn't see a single student who answered that you will give delete some credit. Okay. Now because usually you will say that one insertion I give you $3, $1 for insertion, $1 for expansion, $1 for deletion, etc., right? But that's not enough. Okay, so that the right way is for insertion, maybe you just give him $2, $1 for insertion, and $1 for the extra copy when you expand the table. Okay, and then for deletion, $1 for deletion, another dollar you prepare for the shrinking of the table, because when you delete an element, it's less than 1/4, then it will shrink the table and copy the 1/4 numbers into the new array. So basically, both insertion and deletion, you need to give them some money, and their operation need to contribute some money. So that's why I say for insertion and deletion, even if it's a combined sequence, no matter what kind of insertion and deletion you experience, every operation contribute $2 will be sufficient to afford for all the follow-up operations. Okay, now this is the general idea of proof, but there are some details. For example, actually there is a fourth question which I didn't put it here. I do not intend to make this question too heavy in the midterm, in the formal midterm. So the fourth question actually is the following. So why here deletion has a condition to trigger shrink only for 1/4, only for half, only for 1/4 size. Okay, so why not half? So whenever it becomes half, I delete it. I shrink it. Why I cannot do that? Yeah, so then it will be very easily go back and forth, right? So you insert, you expand, now it's half, right? And then you delete one, shrink. Well, that's not good. Then it's no longer O1, right? If you do this, it's no longer O1. So the O1 time only applies, well, when your deletion threshold, deletion shrinking threshold is smaller or a constant fraction of the expansion threshold. Uh, well, well, I'm not being very accurate, but you know the meaning, right? So you need to uh, somehow store enough money for your shrinking. Okay, so what does it mean? Let me stop the share and share the whiteboard. So for example, now you are here, right? You're around half slots, and then you say, okay, I delete one item, okay, and then delete another item. Now, if you delete item, you accumulate some money, and then at the moment when you reach 1/4, you will have enough money to pay for the copy of the remaining numbers, right? So this is a general idea. This is half threshold. This is 1/4 threshold. Okay, so when you go to them delete and then accumulate enough money, and then accumulate at least 1/4 amount of the current size of array, so much money, and that much money can be used to pay for the shrink, because at the moment when you cross the boundary, you need to pay for the copy of these numbers, right? And then you have enough money to pay. Okay, now if you have less than this amount of deletion and then probably you go back to insertion, you will only accumulate more money, right? Okay, so that there are some details in it, but the general idea is between any shrink and expansion, you will accumulate enough money to pay for the extra copy operations for the remaining numbers in the array. Okay, so this is the general idea. Okay, so any question about question 1? Okay, yeah, so question 2, let me see, there's one question. Oh, 1.2, you still didn't get it. Okay, 1.2. Now remember that we say that whenever yeah, whole sequence. Remember, amortized running time means average running time of n operations. So just now we are proving what? We're proving that whenever you do insertion or deletion, I pay you $2. So overall, if I do n operations, I pay you $2n. And these $2n averaged over n operations will be 2 per operation. So this is O1 amortized running time, right? And then just now I'm explaining why paying $2 is enough, right? $1 is for its own operation, its own insertion. Another dollar is for future copy, right? Future copy operation. Okay, so $1 for its own and $1 for the future shrink or expansion. Suri said, I thought it means the amortized time for a group of sequences of n insert and delete. Oh, okay, yeah, that's you need to look at. You need to also check the delete, right? If it's only about insert, it's easy, right? Or just a continuous insert, and then you just add up these numbers. They will definitely be O1, right? So yeah, so it is for insert and delete. What I'm explaining is for insert and delete. So I mean that there are some technical details inside. I need to show that if for every insert you paid $2, for every delete you also paid $2, and then it will be sufficient to cover all the remaining operations. Oh, okay, I see. Well, so that's the problem of understanding amortized running time. Okay, amortized running time just means average running time of these operations. Okay, yeah. So this is something about amortized. Okay. Ian asked, would we get the detailed midterm answers? Well, I think probably not. Anyway, midterm will not have any overlap with final, except you know what I'm going to say. Except, okay, I will talk about that except very soon. So second question, dynamic TCP acknowledgement. So as some of you said that the question is very long and then you don't have time to read it. Well, actually, it's not very long. So for long questions, usually there will be some useless statement at the beginning. Okay, for this question, the useless statement is the first paragraph. Okay, don't need it. You don't need to read it. You just start from formally. That's it. And then the question is not long. Okay. All right. Only this long. Okay. Well, so so the question is what? Well, the question is, let me again stop the sharing. Share whiteboard. So the question says, in your timeline, you are sending some message at different points. And then you need to, so let me just draw some more. Okay. And then you need to acknowledge them at some point. For example, I say, okay, I acknowledge the messages. And then if I acknowledge after several messages are sent to me, and then my cost is one single acknowledgement cost, this is cost 1, and also its total delay for all the messages you acknowledge at this moment. Okay, so basically you have received some yellow arrows at some point, and then at some moment later you acknowledge using the red arrow. And then your total cost in this phase is acknowledgement cost 1 plus the delay cost of these red arrows, and of these yellow arrows, right? And these yellow arrows delay is just its arrival time towards your acknowledgement time. Okay. All right. Okay. And then similarly, for the second phase, you are computing this, right? And together with this. And then your goal is to what? Is to try to find out where to place the red ones to minimize the overall cost. That's it. That's the problem. Okay. Now, how to do it? Well, so actually, this question asks you to, well, it says that it designs a greedy algorithm. This greedy says, I will keep moving. So it's again moving knife. It's not quite moving knife, but it's kind of moving knife. I'm moving the knife to the right from the first position of the message I received. Okay, I keep moving it. And then when I move this line towards the right, you see that I'm accumulating some delay, right? When I move the line, the delay of the first arrow increases. And when I touch the second arrow, I have one more message experiencing delay, right? So when I move the knife towards the right constantly, and then my delay will be accumulated. And at some moment, when a delay increased to 1, I stop. I say, okay, this is the moment I do acknowledgement. Okay, this is the greedy algorithm. All right. Now you see, well, this is the greedy algorithm, and then the question. So what's the question? The question asks you to, well, if the greedy algorithm did k acknowledgement, and optimal solution did k star acknowledgement, and then first thing, it asks you to show that the optimal solution's delay is at least k minus k star. Is that right? Am I wrong? Yeah, so let's try to see that. Okay, now optimal solution. Okay, now because well, the condition says, so in that question it says if k is larger than k star. All right, if k is larger than k star, then the delay cost of the optimal solution is at least this. So the way to argue is the following. Let's see the blue color. Okay, suppose optimal is something like this. Optimal do acknowledgement here, and then here, and probably here. Right? Maybe I think I'm wrong here. This is not large. This is less. Oh, okay. Okay, so it says that in optimal solution, the delay cost is at least k minus k star. So the reason is actually easy. You see, because the number of blue arrows is smaller than number of red arrows, right? So there must be some red arrows in between blue arrows. For example, it's possible that oh, there is one. So there are some red arrows in between blue arrows like this. Okay, so blue arrows may be this. Okay, so it's possible, right? Otherwise, because you see that the blue one is k star, right? So you have less blue arrows. So red arrows must be somehow squeezing in between blue arrows. And then whenever there are two red arrows, adjacent red arrows in between blue ones, and then you see what's the nature of this gap between red arrows? What's the nature between red arrows? Remember, red arrow says I do some acknowledgement and I wait until at least one delay cost, right? Okay, so that means the things you accumulate in this range has a delay at least one, right? Okay, and then you see this range actually is totally contained in the range bounded by blue arrows, right? Okay, so in other words, optimal solution, which is blue, at this moment, the accumulated delay is at least the delay in this range, for sure, right? So basically, you can see that if optimal solution did less acknowledgement, then his delay must be paid, right? Because what the greedy indication of the delay, some of them will be totally contained in optimal adjacent acknowledgement. And then that will contribute to one delay for each such gap, such pair. And then by some argument, you will know. Let me see. Two A is different. Oh yeah, it is different. I'm being a bit too quick. Okay, so it's like so the description of the first question is there exist k minus k star in indices such that the cost of this delay for those point is at least one, right? Okay, so this is the what I showed you by the map, by the whiteboard here. Right? Okay, so in other words, oh, um, I think I made a mistake. Oh, sorry. I think my TA made a mistake here. Yeah. Yeah, this one is not right. Yeah, so basically the intention is to show that um, the accumulated delay of those points are sufficient to be added on top of the optimal cost. But actually, the description indeed is not accurate, as Ziya pointed out. I will double check that for sure. Yeah. And then, yeah, thank you for pointing this out. This is indeed that. Okay. Yeah, but then, so actually, question 1 is to serve question 2, because question 2 is trying to show that optimal solution, the cost is at least k. K is the number of acknowledgement to use in the greedy solution. All right, and then in the proof you need to divide into 2 cases. If k is larger than k star, then what happens? If k is less than k star, then what happens? Okay, so so if k is larger than k star, which means the greedy solution uses more acknowledgement, then by question A, the optimal delay cost is at least k minus k star. And then adding the k star acknowledgement cost, it will be k. Okay, so in this case, optimal is at least k. Now, if k is less than or equal to k star, and then it's even easier, right? Because your optimal uses more than k acknowledgement, its cost is already at least k. So again, the optimal cost is at least k. And then because greedy, its cost is 2k, right? Because every time you accumulate to 1, you acknowledge once, so 1 plus 1 becomes 2, and then you altogether acknowledge k times, so it's 2k. So greedy has a 2k cost, and then that's why it's a 2 approximation. Okay, and then of course in the question, it assumes that you can go, well, you can always find a point which is whose overall or accumulated delay is exactly 1. That if this is not the case, then you have to find some boundary to decide where to locate that. That will be a bit more tricky. Okay, but so this is only for your information. If, right, so the ideal case is not met, then what will you do, right? Okay, so this is question 2. Now, question 3. Question 3 is a location game. You are locating facilities on a line, and each facility will get the customer who is closest to it. And then, well, if it's equal distance, then they share the customer. So here in the quiz time, many of you asked me whether they can locate at the same place. So the answer is yes. And then when n is odd, then your payoff matrix, you can draw it according to where each facility is. And then in order to find Nash equilibrium, you can find the dominating rows. So here the argument is, for example, the certain columns can be dominated by some other columns. So basically, some players will never choose certain strategies. All right. Now, in other words, you can imagine. Let me share the whiteboard again. So actually, you can imagine if one person's here, one person's here. All right. Now, this guy will never choose some position here because that will only reduce his potential to get customers, right? Earlier, they can divide according to this line, but if you say, I choose this position, then they are dividing about this line, and then definitely I'm losing customers, right? It's not good for me. So basically, you can imagine they will never choose some boundary positions. They will only try to be close to the center. And then eventually, you will know that picking the middle point will be the best solution. Okay, so picking the middle one will be the best solution. All right, and then if it's a even number, 2k, and then you can argue that the kk will be the Nash equilibrium, just using the standard argument about everyone has already get the best benefit without deviating. So if you deviate, you cannot get more. Okay, so I guess this question is a bit standard, just like some of you pointed out. This probably is the second easiest question. The question didn't require proof. Oh, well, it didn't explicitly require proof. Okay, but well, and so the marking is consistent. If you didn't have a proof, then you will lose something. But I guess you are not losing much. Since it's consistent, I think it should be reasonable. All right. Now, just look back at the. Yeah. So usually when we say find the Nash equilibrium, what does it mean? Oh, okay. Yeah. I think so. I think so too. Um, I agree that well, the question should explicitly mention that proof is needed. Um, but but well, one thing I guess you also agree: if a 25-point question, you see, all three sub questions ask you to find Nash equilibrium. Well, but it's possible that some student, now I believe that many of you need to go through those process to analyze, okay, and then but there may also be some exceptional cases. Maybe, well, just by very easy guessing, you come up with a solution, which is Nash equilibrium. All right. So I think that I personally think, well, with a 1/4 of points, the without proof seems not justified to get a full mark. Yeah, and by the way, some of you mentioned the solution. All right, the solution I provide for the assignment. Yes, I did not provide the proof, but it does not mean that the solution is only for your reference. Okay, it's not kind of well, answering that will get full mark. That's not true, right? Okay, so well, feel free to raise your quest to the TA, okay, to see what he thinks. Okay, yeah. So personally, I agree that well, so as I said, right, in some sense, I'm also trying to protect you. The reason is there could be exceptional cases where students can guess the solution, because this one guessing solution is not difficult. Okay, if I just guess a solution, I spend very little time here and spend more time there. If I get full mark here, it will be unfair for many of you. Okay, so this one, yeah, the first one you can guess 01, and that 5 points for sure. I just give it to you, okay, because in the next one there is a proof. Okay, so basically 2 you do not need to give a proof, but 3 you need to give a proof, right? So that's why question 2, so question 1.2, you don't need to give a proof. uh okay, so I'm some questions I will give 3 points to you. Okay, but if you do not want these 3 points, then it's fine. I will make all the questions in final exam not so free. So the problem is question 3. The problem is question 3, all 3 questions. And then, well, they are asking about Nash equilibrium, right? So somehow you need to give some explanation about why they are Nash equilibrium.
Yes, sir, but we didn't require to explain the O1, why we get O1. We didn't
so
explain about.
as I said, you need to explain O1 in the third sub-question, which I'm showing you here. Give your proof for the above amortized running time.
Yeah,
Because
that is the extra 5 points.
Because there is such a question. That's why I do not need you to give the proof here, because the proof is supposed to be given in question 3. And actually, some of you answer question 2 and 3 together. Okay, so you may think 2 and 3 together is worth 10 points, and 5 of them is a guess, and 5 of them is a proof. Yeah, but these two answers, they have different nature. Well, so, well, yeah. Now, as I said, right, everyone has the same amount of time, right? So it's up to you where you devote those time to. And then Nash equilibrium, whether a certain state is Nash equilibrium. Expecting you to provide a proof will be reasonable. Although I admit that, well, maybe explicitly writing it out will be even better. So this one I admit. But, well, adopting the same marking criteria will be fair to all of you. All right? For those who write answers, write argument about the Nash equilibrium there, if they get the same points as those who didn't write, then do you think it is fair? They devote more time there and therefore less time in other questions. Yeah, so I agree with Wing Chong that the question should be more clearer. This one I agree. Okay, and then I would promise that in the final exam, I would not require you to prove something which is not explained that need to be proved. And there is also another question. About why k plus 1 is not Nash equilibrium. I think it should be. This one I need to double check with my TA. I think it should be. If you answer k plus 1 and a k plus 1, it should also be fine. So please send an email to TA to adjust the marking. Okay, so well, I see Siri raised a question about ambiguity of question 1.2, but I do not think it's ambiguity. It's just the definition of amortized running time. Okay, there is no ambiguity issue here. Okay, so I guess well, there's something to improve in the final exam for sure. All right, this one I agree. Okay, now let me just continue a bit. Okay, so you are still watching my PDF, right? Question 4 is a very straightforward question, right? So this question is from assignment, and I believe that so I believe it is very standard. Almost everyone got full mark, so it's a something for free, I think. And then as I said, or as some of you suggested, the for free question will still appear in the final exam. And well, whether it's this one or not, I'm not sure. But there's a for free questions for the question for well, sorry, for final exam. This one I will not explain. It's too easy. And then question 5, stable marriage problem. So for stable marriage problem, actually there is also some so as I said, cooperative game will appear. As some of you suggested, I'm not going to throw it away. It will still be there. All right. And so actually what I'm talking about is those free questions with 3 points. They will appear, even though some I may not mention, but they will still be there. Yeah. Okay. Now stable marriage. Stable marriage. The first one is easy, right? How to check whether it's a stable matching, right? So basically, you just need to show that there's no blocking pair, right? And then I don't know whether my TA require you to give a proof. Did my TA require you to give a proof here? Any comment? Anyone who was deducted points by answering a yes or answering a no? Yeah, finding a blocking pair is a proof. Yes, you find a blocking pair, you say, oh, then it's not a stable matching. Then that's a proof. Okay, so it's similar, right? This question, can you just simply say no? Will you get the full mark? I guess not, right? You would need to find, right? Okay, yeah, I agree too. Nash is not so simple, but yeah, but this I'm only trying to give some example, right? And then second one, find a stable matching by running the Gale-Shapley algorithm. This one is very straightforward. I don't need to explain, right? So because this is standard process. And then next one, construct a 2x2 stable matching and also a 4x4. Now actually, this is the example. So basically, you can construct the examples showing that there are so this is the first one with 2 men and 2 women, and then the case was 4. Okay, so the reason we give this question is try to let you observe the relationship between the original problem and the double size problem. Okay, so you notice that when my TA provide the answer for 4x4, you use A, B, A prime, B prime. So basically, you are copying the identities of earlier problem and also arrange the preference order such that the number of stable matching will be squared. Okay, so the general idea of this question is the following. So let me, yeah, okay, so I guess I can just use this one to explain. So basically, when you copy the instance, you double the instance, you create preference in such a way that the original person prefer original person. Okay, so for example, if originally A prefer B, then in the copied version with A prime, A prefer 2, okay? A prefer 2. And then in the copied version, it will be A prime prefer 2 prime. But then prime will still prefer prime. If you match prime with the original, it will be bad, okay? So basically, 2 will prefer A to A prime, okay? And also A prime will prefer 2 prime to 2. So basically, the original version, they are in their own world. And the copied version, they are living in their own world. If you try to match people from different worlds, it's never good, okay? They will always deviate, okay? So people from different worlds will always be a blocking pair, okay? That's the rationale, okay? People from different worlds, if you match them, then say, okay, the one from the top world, he prefers some partner in the top world. And then the one in the lower world, it also prefers some partner in the lower world. Oh, that's good. That's blocking, right? That's somehow Oh, I mean, well, so not matching them. Okay, if you do not match them, um, that's good, right? So they basically they will so in any stable matching, you will never match such candidates. Okay, and then because the top world has X uh, stable matching, and below world also has X stable matchings, and then you can combine those stable matchings, anyone to anyone below, anyone up to anyone below, and then therefore you have X squared stable matchings all together. So the details, I think you can work it out. It's not that difficult. Okay, so I guess this is the my explanation. You thought part 3 need to prove n equal to 4 with n equal to 2 instead of just giving an example. Okay, so you see that there's a construct an instance, right? So now you're not proving it. You're constructing an instance with 2 people on each side, and then 2 different stable matching. So only giving an instance will be good enough. Okay, so again, there is an instance, right? And yeah, about the proof thing, yeah, we'll make it more explicit for sure. Yeah, and also this question, I guess we can improve the wording by breaking it into 2 sentences. Okay, but anyway, the things that have parsed, well, just let it pass. Okay, so so as long as the marking is fair, I guess your grade will not be affected. So that's the point. So just like some of you suggest that probably for those who give well, proof for Nash equilibrium, we can give them bonus. But for those who didn't, can keep the full mark. But that will not make a difference actually, because anyway it's a very small amount. So eventually, when we decide the range of the grades, it will be the same. So it should be okay to keep with this current marking scheme. And then now I would like to share with you the scope of the final exam. Yeah. Totally agree. So question 5.1, it can be is something stable matching? If yes, give you a reason. If not, find a blocking pair. Perfect. Yeah. So actually, we are making the final exam papers, and we are already doing in that way. Okay. So if this is true, then do what? If that is true, do what? Okay. And then he said, I'm curious about explanation of question 5.2. Draw each step of the algorithm separately. This one I'm not very sure. I think that you need to give the steps, but I'm not sure whether my TA give majority of points to those who simply give out the final answer. This one I'm not quite sure. I will ask him. And now I'm coming to the exam, and the Wing Chun's question I will answer very, very soon. Okay, so I guess they how to say, the scope of the final exam is the one you care most, right? So what I can tell you is, let me just give you very specific hints about the final. So let's start from the algorithms. Now we tested amortized algorithm, tested online algorithm, right? And then so that means I'm not going to test you those anymore. Okay, what I'm going to test you should be, yeah, okay, so here is one bonus point. Okay, although this bonus point is not technical. What do you think I will test you on the final exam about algorithms? Oh, very good. Okay, so Jianheng, you got the bonus. You're the quickest. So approximation. Okay, so I will test you on approximation. Now, of course, this approximation could be combined with DP, greedy. Those are still possible, but definitely I'm going to test you on approximation. Oh, not. Oh, sorry, I made a mistake. It's pay, right? Okay. Okay. Now, second one. Second question. Although I cannot be very sure, but very likely, I will test you still on a cooperative game. If you think that question is some easy questions, right? Okay. So, and then some of you ask me whether approximation would be like in assignment 1. Maybe, I don't know. This one, I don't know. Okay, I didn't make that question yet. I don't know whether it's like assignment 1. Maybe not. Well, but the style could be similar. Right? Okay, so this is first question. Second, well, second question, cooperative game, very likely. Okay, and third question. So there are altogether 5 questions. So I would promise that there are 2 questions that are relatively easy. Okay, it's either very straightforward or very similar as some assignment or tutorial. Okay. Yeah, but then I would like to remind you that yeah, tutorial I didn't release it yet, but what I can tell you is that the second question very likely is related to the guest lecture about auction and matching. Okay, so I'm going to release a tutorial very soon, and you will see some question about VCG mechanism. Okay, so we are going to test on VCG mechanism, and that question is a second question that I consider would be easy. Okay, and these 2 questions will be on easy side, and I believe majority of you can get these 2 easy questions. Yeah. You see, all right. You remember there are only 1 difficult question. You're still right. There's only 1 difficult question. So up to now, I have explained 3 questions. 2 of them are easy. One is medium. Will not be very challenging. Okay, one will be medium. Medium means that very likely for those who solved, who get at least average or close to average, you will be able to solve that one, at least majority of that part. Okay, so yeah, so this is the first 3 questions. Now there are 2 more remaining questions, right? The 2 remaining questions, I can tell you very explicitly which topic it is about. Okay, one question is about fair division. The other question is about facility location, which we will introduce in the next lecture. Okay, so the 2 questions, which one is difficult? I can tell you now. I cannot tell you now. You need to judge when you see the exam paper. But I can tell you that one of them is very challenging, and the other one is moderate. Okay. Yeah, fair division will only be chores. And actually, I have already narrowed down the scope of chores. I will only test you on some picking sequence related questions. Okay, that's it. Nothing else. But concept, I would probably test you like MV3, proportional, MMS. These are all possible. But in terms of algorithm, I'll only test you, give you questions about picking sequence. Third question. Yeah, third question. Oh, Jianheng, you are. Yeah, thank you. Third question is auction and matching topic, and it's specifically I'm testing you on VCG mechanism. Okay. And yeah, two kinds of picking sequences. Yeah, between among within them. Okay, one of the picking sequence things. And then Yuqi asked, yeah, approximation is median. Cooperative game is easy. VCG is easy. The other two, I cannot tell you now. You need to judge by yourself. Okay. This is a very tough question raised by Sri. What is the percentage of students you expect can solve the challenging question? This is very hard to say. Now, well, one thing I need to clarify, right? Challenging questions, it means that if you want to get a full mark, it's very challenging. But it does not say that if you want to get 10 points out of challenging question, it is difficult. Okay, so challenging question is challenging overall. It's very difficult to get full mark, but still you are able to get partial mark. So that's also why it's a bit hard to answer your question. Okay, I would say that maybe only several can get full mark for that challenging question, but more than half students can get 10 points from that question. So this is my intention. Okay, and then Ian asked me what are the difficulty levels of questions in midterm, or easy and medium. Midterm, let me go back to let me share the midterm exam paper again. Where is it? Lost it. I can tell you what questions are considered challenging. So midterm, everyone knows cooperative game is easy question, right? Cooperative is easy question. And then question 3. I would consider question 3 to be easy, but slightly above easy. Okay, so location game is easy, slightly above easy. Now, but it could be comparable to the easy question in final exam for sure. All right, so 3 and 4, 3 and 4, they are easy. 2 is not challenging. Okay, but 2 has some problem, so 2 is not challenging. And then 5, majority is not challenging. The last one may be a bit to the challenging level, but not yet reaching that challenging level. Okay, is already a bit, but we see that the final one is only 5 marks, so it's not that important, right? So not twice. And then the remaining question 1. Question 1, you know, 10 marks are easy. This is challenging. This 5 marks is supposed to be a challenging question. And actually, I believe, I would think this is the comparable to the challenging question in the final. So in the final, well, you see, this question, the proof of the immortalized running time, yeah, so as I said, it's comparable to the final challenging part at the time of your exam, right? And then yeah, and then as I said, midterm only has 1 easy question. The other ones, they are not that not straightforward. Okay, so in the final exam, for those questions, similar as assignment or tutorial or these type of things, and then we will consider them to be easy. So in this sense, final will have more easy questions. Now, as I said, the challenging part, I didn't know it yet because I didn't finish that question yet. Most likely, out of 20 points, 10 points will be challenging. And then now of course, not challenging does not mean it's very easy. Okay, sometimes you also need to try to figure out something. Okay, now but that one I probably will also explain when the time comes. For example, for facility location topic, when I explain that topic, I will also mention which part may appear in the final exam. Okay, so similar parts, or that can be considered as similar parts in the final exam, will be 40 points. Okay, so those points basically everyone can get. So basically, I would expect that in the final exam, everyone can get at least 40. This is something for sure, not like midterm. Okay. Yeah, so so this I explained, right? So easy means you have seen it before in assignments or tutorials, or have seen similar questions in assignment or tutorial. Okay. Or yeah, no randomized algorithm. No randomized algorithm. Okay, I didn't say expected expected average of midterm is 60, and then the eventual mark is 47, right? So if I expect final to have an average of 80, then I expected average will be 67. But that's too high. Okay, I do not think I'm reaching that high. So the description will not be too long. I will try. Yeah. The lowest mark of midterm, this one I cannot release. Sorry, I really cannot release because actually I'm struggling with whether I should release the average and max mean in the canvas, and turns out that it's not that good because they told me that it's some kind of student's privacy. So I'm not going to release lowest. Highest, I think it's okay for me to release. But lowest, no. Okay. Do not include useless information for questions. No, I would try to. I would try not to include useless information. But this is also some ability you need to, well, you do train on. Try to to find out really useful information. Okay, so I guess today's official session is over, but you can stay to ask further questions. Median, it got me. I don't know. Median, let me see. Median. Just take a look. I don't know whether I can find median. Let me try. Median. The data is not here. It's very strange. There's no median data. Let me just count. Oh, okay. So Jiangkun, if you only want to know the lowest mark, whether it's below 30, then I can tell you yes. That's not a personal information. Okay. Oh, this one I can also tell you. How many above 80? 3. Only 3, yeah. Let me count. Wait for me for a moment. I guess the median should be 45. Yeah, median is 45, like some of you guessed, right? Below average. And then oh, okay. How many above average? Because I said median is 45, so that means above average, it'll be less than half, right? So it's likely to be, yeah, less than half. It's 40, maybe 40, 43%, like this, right? And then some of you asked me about 60, right? 60 is 14. So basically, if you are above, you are above, if you are above 60, then very likely you will get A range grade in the end. So this is some message I can give you. So Jiang Kun asked, can we be given some step points? Oh, okay. Step points. So step points, it depends on whether it's really related to the final outcome, right? If it's related to, yes, of course. If it's not related to, then no, right? So because I know that there are also courses where I don't know, maybe yes, maybe no. So no matter what you wrote, you get something like several points. But in my course, it will not happen. Okay, you only write some, well, some meaningful things, right? So something which is really trying to work towards the final direction. Then you will get partial points. That's something for sure. Yeah. Oh yeah. So you should ask. Okay, 40 is something in my mind. All right, you still need to work hard to get 40. Just like a cooperative game one, not everyone is correct totally. Okay, so although everyone is basically, well, basically okay, all right, but does not mean everyone gets full mark for that question. So I would expect that in the final exam, if there's a similar question like this, everyone should get full mark. So this is my expectation. And oh yeah, of course, of course. If there are careless mistakes, then you just compensate that from other questions, right? So there are yeah, about the question based average, I will discuss with my TA too. So yeah, I believe that it's not a big difference. Yeah, so I guess for the topic in the auction slide. I think I will explain that in the next lecture after next week's topic, because next week supposedly we are covering facility location games together with a tutorial, right? So at that time I will let you know what that topic on VCG might be. Okay, so I cannot narrow down to one single problem. That's not possible unless it is cooperative game. So cooperative game, this sharply value thing is something that can be certain, right? But others, I cannot narrow down to one single choice. That's not healthy too, right? Okay. Yeah. We'll I will revise VCG later, for sure, next week. Oh, not revise. Sorry, I'll review VCG. Okay. Yeah. Any other question? Jinchong asks, will the solution for midterm be released? My answer is no. I will not release that solution. I believe that it's already quite clear, and the only unclear things you may work it out by yourself. Okay, so I'm not going to release the solution. And approximation of what? Jianpeng, what do you mean? Approximation of what? Do you mean the question in the final exam? The question in the final exam about approximation, I don't know approximation of what. What I know is it should somehow test you on your understanding of greedy dynamic programming approximation. Okay, in some scenario, which problem setting we'll use, I don't know. But you can use the bin packing problem as some kind of reference, but definitely it will be a totally different framework. Okay. You don't like DP? Actually, DP can be very easy. Oh, I forgot. Does that question has a DP version? I forgot whether I explained that one yet or not. Let me just or maybe not that question. Yeah, DP is not there. Okay. Anyway. Okay, anyway, I didn't decide on which topic to test yet, whether DP or greedy. Fair division is not about consecutive picking, because consecutive picking is in strategy proof, right? We have two picking sequence. One is the IDO instance to general instance. The other one is the picking sequence to guarantee MMS allocation, right? In the ordinal setting. So these are the two picking sequences that may be tested. Okay, so thank you, Jin Song. We are not targeting for the optimal DP. One DP will be sufficient. But anyway, Wing Chong asked about the tutorial question set, what it is about. Okay, so tutorial question, basically, there are three questions. One question is on, let me see. Yeah, one question is on VCG mechanism, all right? And the second question is on facility location. And then third question. So actually that facilitation question has something to do with the final two. Okay. In some sense. And then the last question is on scheduling. Okay. Although we are not testing on scheduling, but I still hope that you will know something about that. And then so that means that question actually we are not going to explain until week 14. Okay, so I will only explain 2 questions next week. And yeah, I think that now we have 3 in-class questions now, and together with 3 tutorial questions in the next week. Tutorial question I will release early next week. Okay, so now please focus on assignment 3. Oh, by the way, assignment 3, I'm just doing a survey, okay? How many of you have finished assignment 3? Because I'm going to do some small adjustment of assignment 3. Did anyone finish both Q2 and Q3? Did anyone finish both Q2 and Q3? Okay, if not, then I would change the requirement to be finishing 2 questions instead of 3. So 1 and 1 of 2 and 3. So which basically is about between 2 and 3, you only need to choose 1 question. Yeah, you're right. Q2, Q3 we didn't teach yet, so we'll teach next week. So that's good. That's why I can still make adjustment, right? So basically assignment 3, between Q2 and Q3, you only need to do 1. Okay, so 1 of the Q2 and Q3, and 1 is Q1, and then that will be the whole set. And then OJ deadline is 2 days after the original deadline, because the online judge is experiencing some problem in the beginning of this week. So that's why we postpone the deadline by 2 days. So let me see, when is that? So OJ deadline is April 12th. Yeah, you're right. Okay, and then actually some Wing Chong asked me any hints on assignment 3 Q1, right? So there is one hint. So basically Q1 is asking for some proof, and then it is referring to another paper, and that another paper is proving a similar property, not similar, a related property with a quite complicated procedures. And the hint is to prove the new result in Q1, you only need to use some easy steps from that proof, not the whole set of steps. So so the earlier two steps probably will be sufficient. Okay, so basically that's the hint I can give you. And then okay, well, you can take some time to figure out about the 1/4. And then and Dutlef asked if we finish OJ, then we only need to submit 1 assignment. Yes, you're right. But you can also well actually you already made decision for assignment 1 and assignment 2, right? So OJ will account for 2 assignments, but these 2 assignments bear the same marks. So theoretically, it's true that you only need to submit 1 assignment, but you can also submit 2, because in case you think your OJ, for example, you solve 4 questions out of 5, then you only get 80, and probably the other 2 assignments you submitted is 84 and 86, and then you can still consider it to be 86, 84, 80, right? it's better than 84, better than 86, 80, 80.
Yes, sir. Can you hear me?
Please.
Yeah, you just said that in assignment 3, we just need to choose one from question 2 and question 3, right? Okay, thank you.
You're right. Yeah. Okay. So that means in assignment 3, you need to work. You need to solve 2 questions altogether, right? Okay. The picking sequence, right? In the fair division topic, one is the picking sequence in transforming ideal solution to general instance solution. Okay. And the other one is the picking sequence about the case when you only know ordinal preference, and then you ask agents to pick items by turns, and then how to guarantee that they still achieve good MMS allocation. But of course, MMS only a reference. Okay, so it's only one fairness measure. We may also test you on other fairness measure like free, proportional, right? Approximation on MMS, will it be tested? Very likely not. That's too complicated. I'm not going to test you a very complicated fairness measure. And also, I'm asking you to think about the picking sequence of 1 to 2, right? Why it gives you 4/3 approximation. I'm also going to explain that in the next lecture, but I hope that before that you may have some idea. Okay. Yeah, so the order of for ideal to generate general case. So that's the, well, the ordinal ideal sequence. You have an order of items with decreasing cost, right? You will use the order. So actually, it's not a picking. It's not quite a picking sequence, but it's just specify the order that the agent will pick items from the general instance, right? So it's the most elegant algorithm I promised you last time, right? Yes. So the second one will be sequence picking on partial information. You're right. Minimum total cost or minimum piecewise cost. So Jianchong, what so actually I'm talking about that one. Let me share the screen. So yeah, so one picking sequence is here, right? You use the order of these cost to let the agent pick, right? So A3 pick these 3 items, and then agent 2 pick these 2, and agent 3 pick this. This is the one picking sequence. The other one is the other one is this one, right? Picking sequence like this. So Jianchong, is it okay now? So this is the second picking sequence I'm talking about. And then Wing Chong asked, do you need to know how to find prop X allocation for IDO? That would be too easy, right? That's something I already explained. I will not test you on something I already explained. Challenging question means that based on those, you need to derive more, right? First sequence A1 and A2 who? Oh, okay. You mean first sequence is this one. Okay. So in this example, A2 will pick first. So after A3, pick 3 items. A2 will pick the next 2 items, and A1 will pick the last item. So this is the first picking sequence. So yeah, according to piecewise cost. So you see that in the second figure, right? The cost agent 3 receives is the smallest, 333, 111, right? So therefore he got the he can pick items. He can pick 3 items at the very beginning, right? So that's why he picked this one, this one, this one, right? So Wing Chong, what's your question? Which algorithm is that for IDO? Yeah, so this oh, you mean prop X allocation for IDO? Okay, so remember that we explained that any EFX allocation is prop X. So we are simply using EFX allocation for IDO instance. And the EFX can be very easily found by top in MV cycle elimination and also by those follow-up algorithms, right? Okay. In this example, the prop X allocation is just this one, right? The agent 3 got 3 items, and agent 2 got 2 items, and agent 1 got 1 item. Sorry, there's some noise here. So did I answer your question? In this example, right? It's just the red circles. Yeah, it's not given by specific algorithm. Sorry, I didn't make myself clear. So, or maybe it is given by specific algorithm, but may not be. Okay, so it's just some allocation which is proportional X. Yes, you're right. Okay. Yeah. Any other questions? Okay. Ian asked about QE question. Is it all challenging? Definitely not, right? Among the 50 points, I bet that there are at least 20 or yeah, at least 20 that will be easy. Okay. And then the next, probably the next 20 will be medium. And then the last 10 will be challenging. Usually it will be this style. And then so as I said, Q1.3 is challenging. For the first time you see the question, it is definitely challenging. I will consider this as a challenging question. It belongs to the last 10. Sequence picking question will it appear in the tutorial? So I guess that I said that I will explain that 1 to 2, why it is 4/3. I will explain that in the next week's tutorial. Okay. Yeah, no worry. You will see the questions very soon, early next week. Okay. Yeah. So the second type of sequence picking you said it's related to prox MMS, but it may also relate to other fairness measures. Okay, so it's just like well, it's just well, I'm just I'm just explaining that the picking sequence. This is a topic. Whether it is applied to proportional, MV3, or MMS, it depends. But well, yeah. So I said I will not test you on approx MMS. Okay, it's still true. Okay. No, then it's not possible. Okay, so I can only show you. I can only show you approx MMS. I will not show you other things. Otherwise, it will not be challenging, right? So suppose, well, otherwise it cannot be challenging. So because it's one of the two candidates for challenging question, well, I cannot make it too similar to what I explained in tutorial, right? Yes, fairness measure will be what you learned before. This is something for sure. Yeah, those EF1, EFX, prop1, prop X, right? So these things. And very likely I will also give the definition of those fairness measure. You don't need to memorize that. But of course, I guess it's not difficult. Just for completeness, I will put the definition there. So if you have the definition, then the question could be long. But if you already know the meaning of the definition, you don't need to read the definitions, right? So those are only for helping those who, well, want to double check whether your understanding is correct. Okay, any other questions? I will release the tutorial question early next week, sometime like Tuesday, probably. So actually, I can already release the tutorial question without the last one. Okay? As I said, there is also a question which I will cover in week 14. Without that question, I can release it earlier. So maybe I will just release an incomplete version first. Okay. So no other questions? Then yeah, see you next week. And actually, next week, I believe that that lecture will be the most interesting one. Maybe. Okay. So see you there next Thursday. Okay. Thank you. Yes, next week we'll have revision. But actually, I've already did revision today for some topics, right? So next week we'll just complete the remaining part. So it's very easy, easy revision. Yeah. Thank you.